So we're going to study Boltzmann distribution today. So let us consider. There are n particles. Okay, so let's consider there are n particles in a box. Now we also know that these n particles will have different energies, E1, E2, E3, E4, and so on. So if we consider now, okay, so let me just draw a box here. Let me just draw a box, and there are some energies here in the box. Excuse me, there are some particles here in the box. Okay. And what I will do is I will give each of these particles an energy, and I'm compartmentalizing these particles. Okay. The way how I'm doing it is something like this. I'm considering that there are n1 particles. Okay. There are n1 particles having E1 energy. Okay. And then there are n2 particles having E2 energies, and so on. So in short, what we can write is summation, okay, of I equals to 1, sum over to the number of compartmentalization, is basically an EI. Okay, so that's the energy that we have of a system where there are n particles. And we also know that then, let us say this energy is then E. Okay, and we also know that the number of particles has to be fixed, right? N3 and so on. So this has to be fixed, and what I will say is I equals to 1 to the number of compartmentalization and summation of n I, that's n. So these two are the constraint of this particular system. Okay. Now what Boltzmann literally tried to do was, based on these constraints, he tried to find the distribution of the particles having certain energies. Okay, so he basically wanted to find how many particles would be there in a given energy state. Okay, so remember that we have compartmentalized this energies here. Okay, and we are just saying there are n1 particles, n2 particles, and so on. So before we move on, we also have to know something about the thermodynamic probability. Okay, or let me just say this. Let us say this. So let us move on to the new page here. Okay, so basically what I'm saying is this. Let's say I have n1 particle, excuse me. So let's say I have 3 compartments here like this. This compartment has energy E1, this compartment has energy E2, this compartment has energy E3, and so on. Okay, and what I'm also saying is there are particles here, right? There are particles here, there are particles here, there are particles here, and so on. Boltzmann basically wanted to understand that the amount of, he just wanted to understand the function that was describing these particular situations. Okay, basically was trying to find the distributions of particles in various energy levels. Now, we should understand something called a possible number of microstates given a macrostate. Okay, so let us say, let us define a variable omega. Okay, And what I will say is this: the possible number of arrangements of all of these particles is what is called n factorial divided by n1 factorial, n2 factorial, n3 factorial, and so on, right? So you can think of something like this. Okay, so let us say we have a system, we have a we have number of sweets. Okay, so let's say we have Kit Kat, and let's say we have a dairy milk, and maybe Rochefort, and so on. Now, if I say how many particular arrangements are there in this particular situation here, how many arrangements possible here? So obviously, because these are repeated, okay, we can say that there are, count the number of particles here. So how many particles here? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 particles here. So normally when everything is different, all the chocolates are different, we say that there are 8 factorials possible arrangements. But if some of them are repeated, okay, then what we say is we divide by those repeated numbers. So we have like 3 factorials, and 2 factorials. Yeah. So this is the possible arrangements, possible number of arrangements. Okay, so these are the possible number of arrangements in this case here. Now what we are doing here is basically we're looking at the compartmentalization, right? So in this particular case, we could say this compartment is E1, E2, E3, and so on. So the number of possible microstate here is this, isn't it? Because there are n particles, right? All of the particles are n particles, and because these compartments has the same energy, all of the particles in this has the same energy, so it has divided by n1 factorial, and similarly n2 factorial and n3 factorial, and so on. Now, so this is what our microstate is, okay? So the possible microstates in the system that we are considering here. Now, what we are basically doing is now we're trying to maximize the microstate. We're just trying to look at maximizing the microstate given those two constraints that we already wrote it down, right? So the two constant was basically saying summation I NiEi equals to the total energy, and summation of I Ni is n. So the thing is this: based on these two constraints, okay, so based on these two constraints, Boltzmann tried to find a distribution. Now, it would be very difficult for us to maximize this in the way it is. Okay, so what we basically do is we basically try to maximize this by maximizing the log function instead of the omega function here. So we try to maximize something called a log function. Okay, so we just write ln omega. So we try to maximize this because this is a monotonic functions. Okay, so I can write this as then, by using the log rule, I can write this as n factorial minus summation of ln and I factorial here, like this, right? So now our problem basically is then to maximize this function here given these constraints. So that's what we will do next. Okay. Now, it's also important if you know something of a Lagrange multiplier. If you know something about the Lagrange multiplier, then it's going to be very easy. So what I will basically do is this. Oh, before that, let me also tell you that there is an approximation that we will use here. And that approximation is the Stirling's approximation. Okay, which basically states that Ln factorial is n ln n minus n. So this is the Stirling's approximation. Okay, so I'll just write this at the side here. So let me just move this to the side. Okay, let me erase it. So just remember, no, let me write this on the side because we need it. So let's say Stirling's approximation, Stirling's approximations. Okay, and it's just ln n factorial is n ln n minus n. Okay, so let us continue with our derivation here. So let me erase this one here. Now also, let me just tell you this one. I mean, you have these two functions now. So ln omega is just ln n factorial minus summation I ln ni factorial, right? So something like that. You have these functions here. So let us use Stirling's approximation here, and then maybe we'll apply the Lagrange multiplier after that. So in this case, this simply becomes n ln n minus summation of I. This becomes ni ln ni minus ni. Oops, excuse me. So we've missed something here, right? So this simply becomes n ln n minus n. Okay, so and this becomes n ln n minus n minus summation of I and I. Oh, by the way, this is in a bracket here, so n I plus summation of I and I. Now we also know that this quantity here is simply n, right? So I will write that as n, and maybe this 2 will get cancelled. So I'll just write this as n. I'll just write that as n, and you see here that this 2 gets cancelled here, plus and minus, and finally we have this as n ln n minus summation of I and I ln ni. So this is our ln omega. Okay, so let us say this is the function that we have, our main function, and also we have our constraint as this summation I and I equals to n, and summation I and I epsilon I equals to e. So these are the two constants. So based on these two constants, we have to maximize the function that's here. Okay, so let us move on to the Lagrange multiplier. Now these, I mean, given a constraint, if you want to maximize a function, then the only sensible way to do is by using a Lagrange multiplier, and it's a very powerful technique. Okay, so what we basically do here is then this. Let me erase this part here. oops, excuse me, let me add new page here. And now Lagrange multiplier basically tells us this, that if you have a function that you want to maximize, okay, if you want to maximize a function, then the gradient of your function that you have to maximize will basically be equal to some constant, okay, some constant times the gradient of the function, one of the constraints, okay. And if you have more constraints, then maybe add those constraints too. Okay, so this basically becomes gradient of j and I e I. So this is a Lagrange multiplier. Okay, now what do we do now? Now we open up. We will do step by step. Okay, so first of all, we'll do only this part here. So let me try to finish it in this page here. So we know that ln omega is n ln n minus ni summation of I and I, oops, excuse me, so ln and I, right? Now let us find a gradient. So gradient is basically a partial with respect to j ln omega, right? So this is the thing. So if we take a partial here, so it just becomes delta n, so n ln n times delta n over delta nj. Excuse me, I have to write nj here. So this is nj minus summation of I delta of delta nj and I and then ni. So this is the partial that we have to do. So this is just a two-step process, and when we're done, so the first thing, what happens here is this just becomes n 1 over n using the product rule, right? So this is ln n, and this becomes delta n over delta nj minus summation of I. So partial derivative is basically taking a derivative with respect to some particular variable, right? Now here nj is basically a variable that is fixed variable, right? So when I equals to j, then we say that when I equals to j, we say that this simply becomes 1 plus 1 plus n of j, excuse me, ln of n j. So that's what we have here. Okay, so if you want to write one more step here, so you can just say this is 1 plus ln n bracket delta n over delta nj partial minus, this just becomes, now because the I equals to j is just one term, so I don't have to include that anymore, so this just becomes ln nj. Okay, so this is the thing that you have to remember now. So this is delta over delta nj ln omega here. Now let me just go to the new page here. and maybe let's try to simplify, okay? Now what we can do is basically, now we have to take a partial of j of, excuse me, we have the term on the right, right? So this is summation I and I. Okay, now we're taking a partial of j, so this is just alpha delta over delta and j. Now again, the only terms that we have is when n equals to I equals to j, so this is j, so this just becomes alpha. Similarly, the beta terms here, the second term is partial of j, summation of I, and I, so this just becomes beta, and again here I equals to j, so this just becomes delta of and j, and then this is ej, so this just becomes beta ej. Okay, so this is the case when, excuse me, this is I, this is j. Now we already have on the second, the right hand side formulation, right? So then our formula is basically this. What we basically have is this now. Okay, we basically have this. So 1 plus ln n bracket delta n over delta n j minus 1 minus ln n j equals to this 2, right? So that's alpha plus beta ej. Now what do we do about this term here now? Okay, now again remember that we had a constant, right? So we had a constant where summation of ni I was n. So if you take a partial here, so delta n over delta nj, so you can see that the only time it will make sense is when it is delta nj over delta nj, right? So this is 1. So we see that delta n over delta nj is just 1. So this term here simply is 1. Okay? Now let us just substitute it and then check if that makes sense here. Okay, so when I'm substituting, what happens is basically it reduces to this now. Now we're almost done with the derivation. So this just becomes 1 plus ln n minus 1 minus ln nj equals to alpha plus beta ej epsilon j. So here 1 gets cancelled out, right? So 1 gets cancelled out here, and remaining term, just let me just rearrange and write it so that it's easier to visualize here. So I can put the right hand to the left side, and then I can write here ln nj over n. So then this basically gives me nj equals to n times e to the minus alpha minus beta ej. Now this is sort of a distribution that we were looking for. So this is a distribution that Boltzmann came up with, and it's pretty interesting to know that the number of particles, okay, having energy Ej is given by this. Now the only difference here, now the only thing is we are left to find the constant alpha and beta, right? So it's not too difficult to find alpha, and so we'll do it immediately. So what if I now do summation? I add summation on both sides, nj and summation of j e to the minus alpha minus bej. What if I do that? So the left side is obviously n, right? So I can write this as n equals to n. Now because the alpha doesn't have a j dependence, I can write e to the minus alpha here. And I can write this as e to the minus beta ej, epsilon j. Okay, so now I can just divide both sides by n, and I can come up with an equation that's this: e to the power minus alpha equals to e to the power minus beta ej. Okay, so this means, excuse me, e to the alpha equals to e to the power minus, oops, excuse me, I made a mistake here. There must be a summation here, right? So this is just a summation of j. Okay, so I have to write a summation here, otherwise it's not correct. And what I get finally is e to the alpha is basically summation of j e to the power minus beta ej. So this is called a partition function. Okay, so I represent it by q. So this is also called a partition function, and if I rewrite the formula here, then I basically have this one here. We had nj to be n times e to the power negative e alpha, negative beta, epsilon j, and I can rewrite it to say nj over n equals to e to the minus beta alpha j divided by e to the alpha, and we also know that e to the alpha is going to be, it's going to be summation of j e to the power minus beta ej. Okay, now what basically is this, right? So this is a sort of probability function here. So this is also called a Boltzmann distribution, okay, in terms of probability. So what it's basically saying is the probability that a particle is in a kth term, okay, excuse me, the particle having energy Ej is basically e to the minus beta Ej over summation j e to the minus beta Ej. So this is a probability distribution of a particle having certain energy Ej. Okay, so this is the Boltzmann distribution then. This is all about the Boltzmann distribution. Okay, thank you for watching, and I hope to publish the next lecture soon.